Hello, this is a quick video conference on Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle, or at least one way to represent the principle, is as follows. We have delta x, or the uncertainty in a position x, as a product with delta p, or the uncertainty in a momentum p, must always be greater than or equal to a small number which is equal to h bar over 2. What this says is that we cannot simultaneously know position x and momentum p for subatomic particles such as electrons. So I'm forbidden from knowing the exact location and the momentum of an electron. As chemists, we're interested in electrons, and electrons we know are wave particles. So let's ignore the particular idea of an electron for a minute, and let's focus on the idea of a wave electron. Waves are governed by wave equations. So let's look at the basic wave equation for an electron. A wave equation has a symbol psi, and we want the wave equation for constant momentum at a location x. And this is equal to a constant, let's call the constant a. The constant for our purposes is not really important. It's a constant a, but this constant has an exponential factor, e to the I dx over h bar. I here is an imaginary number, p is momentum, x is position, and h bar is a very small number, the same h bar as we saw up here. Now this looks complicated. It's actually a complex wave equation. We know it's complex because it has the complex number I. But we can circumvent all of this complexity, and we can figure out a way to use this equation to tell us something very interesting and cool about the electron. The way we've described the wave equation, we're saying a constant p, constant momentum. So this constant momentum implies the change in momentum is 0. Because by definition, constants don't change. So a constant momentum implies that the change in momentum is 0. Well, we know from Heisenberg that we don't know the product of both at the same time, or the product of both must be greater than a very small number. If one of them is 0, then the other must approach infinity. So this implies that the location must be known to be somewhere in infinity. So in other words, we don't know where the position is. If I exactly know the momentum, I don't know exactly where the position is. It can be anywhere in an infinite space. How can I marry the wave equation with Heisenberg? How can I convince myself that both equations are talking about the same phenomenon? Well, the trick is to square the wave function. We need to square the wave function. The wave function alone has no physical representation, so we have to square it. So let's square everything in the wave equation. We take the wave equation and we square it. That means we square the constant. And then we square the exponential components. So this is e to the I px over h bar. minus IPX over H bar. If you're not too familiar with I's and imaginary numbers, to be honest, it's not that important at this level in chemistry. But when we square them, one of the I's will have a plus value and one of the I's will have a negative value. So we've got an exponential with one variable minus another variable. So this is just going to equal a squared e to the 0. Because something minus itself is 0. Well, e to the 0 gives us 1, and we have our constant. So we have one multiple of the constant. So because this is a constant, that means we have no idea where it is. And it agrees with this. I'll erase the board and I'll give you a graphical representation that will drive home this message. On a graph, if we plot the square of our wave function against location, we arrived at a constant value. So this is our constant. And as you can see, we have no idea at which location the electron is because it looks like the electron is everywhere. So it appears that the electron is everywhere. So it could be in an infinite amount of places simultaneously. Obviously, the electron is somewhere, but our mission with this short video was to explain how, by interpreting the square of the wave function, it would appear as if the electron is everywhere, and this agrees with Heisenberg's uncertainty principle. We'll have subsequent videos where we'll look a bit more and in a bit more detail at Heisenberg's uncertainty principle. For now, enjoy the mystery of Heisenberg.